like I said, I did my project out at MDRS, and the main reason for that was radio isolation and the limitations of simulation, as well as the harsh environment. When I say radio isolation, there were three main sources of radio interference out at MDRS, which is the two cell phone towers behind the gas station, as well as the Hanksville Hanksville Airport. It's nowhere near international. The limitations of simulation were things that you really don't consider, such as typing with gloves on or having a helmet on that just cause problems. And then the harsh environment is things such as just static electricity that builds up because of the dry environment, and the corrosion on the physical connections due to just the environment. So radio astronomy in general can kind of be broken down into why we do it into a few different categories. There's danger and discovery. With radio astronomy, it's really good for monitoring solar activity and things like meteors. You can track them with radio astronomy, and it's really useful with going to Mars. That you would want to know where a giant rock is flying at you, or when a mass coronal ejection is going to come at you as well. So that was some of the main interest for MDRS on why we would need this. Then discovery, you want to know things that really can't be seen on telescopes of the optical type. Because you can't see big clouds of neutral hydrogen. Hydrogen is invisible. And with a radio telescope, you can actually map it out using radio frequency. So it really does help in that respect. In general, the size requirement is one of the main issues for radio telescopes as they are. Things such as this telescope in Puerto Rico is something that I definitely want to avoid, partially because budget limitations and size limitations. Can't take that on a plane. A lot of them use helium cooling, which is getting really expensive, it's getting really rare, and it's a very specific use. You can't use helium for much else, especially liquid helium. Like I said, it's really specialized equipment. A low noise block for the Haystack Observatory isn't going to be able to transfer over to a different observatory. It's all going to be specific to that one installation, and it's all really fragile. If you drop the low noise block or any filter, you're going to need a new one, and it's going to be really bad. Also, underfunding causes a lot of issues. With the SETI's budget being cut recently, well, not recently, but it has been cut quite a bit. Their installations have been very underfunded. So the previous equipment at MDRS was a radio jobe, which is used to observe Jupiter at about the 20 megahertz, which in itself was great. But it did have a few issues. It didn't really interface with the Musk Observatory. So you had two great instruments out there that just weren't interfacing at all. And though I wasn't able to address that in mine, I do believe there is some room for something there. It was also really omnidirectional. So any form of interference was really hard to take out. With things like satellite dishes, parabolic reflectors, you can be behind the reflector to reduce some of the interference. With an omnidirectional antenna, anything around it's going to cause a lot of problems. And the final reason I didn't really do anything with it was because it was taken down before it went out there. So the main problems with it, as far as radio astronomy for me, is it's really inaccessible. Like I said, size requirements, budget constraints. It's also really heavy, really fragile. They don't let you take big, heavy black boxes onto airplanes anymore. TSA gets really mad. And it's also really fragile. Not only whenever you're going to Mars, you're going to have heavy landings. It's not going to be the most comfortable thing. And baggage claim people, because we did fly on airplanes, like to throw boxes around. So there was that. Equipment's definitely difficult to maintain when it's hyper-specialized. You know, a 3-month lead time on something really does cause problems when you're wondering, hey, is that mass coronal ejection coming at me? Am I going to be irradiated? What's going to happen? And like I said, it's really single purpose. Liquid helium, it's great for cooling things, but liquid hydrogen, liquid oxygen is much better for other uses such as, fuel, water, other uses. So the goal is to establish a cost-effective temporary radio telescope. That's kind of what I was mainly going towards. I wanted to record data on solar activity and then observe environmental challenges and locate unintended sources of interference. And mostly on the last one, to kind of address that, I went on the FCC's website and kind of mapped out all of the local sources of interference to kind of see what would cause any problems. And like I said, there were mainly 3 big sources of interference. Past that, it was pretty limited. Environmental challenges was mostly physical corrosion, static electricity, things that would really only be present on MDRS or on Mars. So the concept is loosely based on Mark Spencer's Build a Home for Telescope article that was written in the ARL magazine a long time ago. But with that, it was fairly rudimentary, had very low resolution, and you weren't really able to analyze the frequencies and if you wanted to. So that was not really scalable. Improvements from there, I wanted it to better reflect the industry uses. With the original concept, it wasn't really tuned to a frequency that was useful. Mine is around the hydrogen band, which is 1.42 gigahertz. It's what SETI observes on, and it's also how you map neutral hydrogen clouds. I wanted a more directional antenna. Like I said, omnidirectional antennas are really easy to interfere with. And they need to be less weight, like I have here. It's a really loose estimate, but about 50 pounds is almost $1 million to get into the air. So that's a bit of money. So any weight cut is much better. And with the Joe, it was mostly PVC pipes hung about with wire, which isn't really able to withstand 180-mile-an-hour winds that could be present on Mars. And I wanted really readily accessible parts, so things like DigiKey mouse, those were my main sources for parts if I could. So primary research material, that's basically what I used. The ARL handbook was great for showing the super heterodyne receiver, which was what my project was based on, and the amateur radio astronomy just kind of supplemented that. As far as purchasing equipment went, I really wanted to go with common component suppliers, like I've said multiple times before, and over-specialized parts were a problem. Using a guy out of California in his garage can cause a lot of issues, there's a lot of lead time, and just you can't order in bulk. And then the requirements amongst all of the parts is they need to be at about 50 ohms, low noise levels. It's hard to know what you're observing when your internal noise level is covering up what you're supposed to look at. And then a low manufacturing tolerance. You want your oscillator to be oscillating at the right frequency. So the original equipment I used was the Dish 500 satellite, which is actually a very common satellite dish. It's 19 inches in diameter. It's originally intended to operate around the 12 gigahertz frequency, which is way above what I normally did. So I went through, took out the low noise block, and just used the feed horn to kind of capture the signal, and then did my processing elsewhere. And with that, my data acquisition unit with MIDAC, basically it was because it's one of the few data acquisition units that didn't use pulse width modulation to do any analog signals, as well as the lab view environment is just much better to use than some of the smaller ones. So just getting into some of the component size, the filter was for mini circuits. It was about 50 ohms, and it's band pass of around 1 gigahertz to 2.2. And basically that was just to filter out any FM, TV, as well as cell phone, because cell phones are generally around 915 megahertz, so it kind of cut out that band. From there, the low noise amplifier, I had two options. Originally I started off with the Algo, and I was going to build it, but due to time constraints and surface mounted components being a pain, I decided to go with something that was a little more reliable, like the mini circuits. It had a more constrained range. With the original one, it was very broad in its range, and kind of, it would introduce a lot more interference. With the other one, it was much more constrained and had a larger gain to noise ratio. So from there, the voltage controlled oscillator, which is a really important part of the super heterodyne receiver to mix it down, was the POS 1400A with a good frequency range that would allow me to make something down that the MIDAC could analyze, because getting something to analyze a frequency of around 1 gigahertz is extremely expensive. So that was the main thing I ran into. As well as it was tuned from 10 to 20 volts linearly, where the MIDAC outputted 1 to 10. So I had to adjust that with an amplifier, and the output was fairly decent. The mixer on that was also from mini circuits, which is a very common microwave supplier for components. And it had a decent frequency range that did allow for down converting of the signal that I was looking for. And the loss conversion was a little high for what I was looking for, but it wasn't bad. In the assembly altogether, I tried to use RG58 cable, something that's really common. It's like when cable companies started using RG6, it dropped in price. I wanted to use cables like that, nothing too rigid and expensive. With regular SMA connectors, a large ground plane, and very modular. So if the filter went out, you could replace replace the filter, and it kept the prices down. It was put in an enclosure that was supposedly sand resistant and dust resistant, which I later figured out wasn't all that much. And it was very static resistant, mostly just user kind of being cognizant of static electricity, frying nice circuits like that. So there's a diagram of it, which is way lighter than I thought it would be. So originally you take your RF signal in, it goes to the high pass filter to kind of knock out any cell phone signals, things like that that would overshadow it. Passes it to a low noise amplifier, which then sits at the mixer, while from the other side, the MIDAC was controlling an amplifier, which would then tune the oscillator, which would put a signal through to the mixer. It would combine the signals, producing an image frequency that was much lower. From there, you kind of see what it looks like. It's not quite as neatly organized, but that is what it's doing in a nutshell. The code that I used was written by Larry Benton. It was built in LabVIEW. It does two things. It controls the voltage-controlled oscillator as well as analyzes the graph. The analyzing part of it is not as full as I would like it to be, but it is part of the work in progress. So the voltage-controlled oscillator part was tuned for looping the voltages and just stopping where you found the best response, and then just clocking out exactly where that voltage was in the oscillation. And like I said, it was outputted through the MIDAC, which is an actual signal. The data analysis was graphed raw, though I would like to incorporate a fast Fourier transform eventually. At the moment, it does not have one in there. As you can see from the graph, it was not the highest resolution, but there was a little resolution, which was nice. Like I said, I used it to observe the sun. Really low resolution. When put away from the sun or a strong source, you get a little internal noise with extra, and then followed by some more amplitude, some more data whenever it was pointed towards the sun. So you really need a larger dish. Though 19 inches is semi-large for what you would want to take, it would be best to have an interferometer, which would be multiple units stacked together. It allows for better flexibility as well as just higher resolution. I needed a more stable power supply. My power sources there kind of let me down, so I had to improvise something. And better sealed equipment. Sand dust over time would have caused a huge issue with this project. Though in the time that I was out there, it didn't. I got very lucky. More precise aiming method. Past just aiming it at the sun, you need to have better forms of aiming it whenever you have more resolution, so know exactly where you are pointing. And then incorporate more frequency analysis, fast Fourier transforms, things like that. Such. And like I said, in the Martian context, you need lighter materials. It's a heavy 50-pound dish is going to cost way more than a 25-pound dish. Just obvious in that. Solar power sources would be awesome for it. You would have to have a battery bank backing that up, but things along those lines, and very long line based interferometer. In the future for the project as I see it, I would like to look more into NASA. They have released a PDF on radio propagation on Mars and how the methane atmosphere affects that, which I would like to kind of analyze and see how that would affect my project. Get a more stable power supply, better battery banks, I guess, and voltage regulators, more assemblies for interferometers, so adding a few more, making it more flexible, more resolution. The possibility of using celestial sources as clocks for the interferometer. In larger ones, they use pulsars and quasars actually as knowing the clocks, so you know the period of that, so you can use that to figure out if your units are in time. And from there, that would allow you to have better resolution. And then I would also like to have more precisely measured internal noise. So I didn't really have the time nor the money to actually look into what the internal noise was. So most of it was hoping and assuming that the internal noise was fairly low. From what I'd seen and what I could put together, it wasn't too high, but there was no way of knowing exactly what it was. So I guess questions and answers now. So any questions? Yes.
I heard you use the word fast Fourier transform a couple times. What were you doing with them?
So it was more for frequency analysis. What I had right there was mostly just plotting the frequency versus the amplitude. But I didn't really know, what was coming in at 1.42 gigahertz or any harmonics of that. I needed to have a better analyzing of what was coming in.
Well, I'm not electrical engineer, but when you're using it, you get some kind of spatial information.
What was that?
Well, I've used fast forward and transform this to get in optics to get spatial information.
From the way I understand it, and I could be wrong on this,
You showed one. Did you show an array of something there once?
Yes, with these, that was just the raw data itself, without any
Did you use those transforms on that?
No, sir, not yet. I do have the program written, but I haven't actually been able to implement it yet due to time constraints. With it, though, it would yield something similar to a histograph, which they use a lot in camera photography, oddly enough, but it would look similar to that.
But it would give you some picture of what you were looking for, right?
I believe so, yes, sir.
And now you said you tested this. Was it at the Utah station?
Yes, sir, at MDRS in Hanksville, Utah.
Oh, and you had problems with handling it, so it's very flimsy, is that it?
Yeah, there were a lot of issues out there. Power supply issues, just not having a good setup for it. Where I originally planned on basing it didn't work out so well, so it was a lot of flexibility that had to be incorporated into it.
You're also basically developing this to have a hand carry system, is that right?
It did actually all fit into my backpack, so anywhere I needed to go.
Yeah, but it's a portable system what you're trying to develop.
Essentially, yes.
All the radio astronomy we do on this Earth, or there's one in Puerto Rico, isn't there?
Yes.
And there's a whole bunch of them out there in the desert somewhere, New Sonora, right? But those are stationary things, even though they can roll them around and stuff. But you want something portable. Now, where are we going to use that when you get?
So, just simple terrestrial applications on Earth would be things like putting it at colleges. It would be extremely useful because a few colleges want to spend the time or the money to throw a bunch of money behind giant telescopes like radio
What's
telescopes.
going to be the application, I guess I'm asking?
At MDRS, or do you mean at Mars, or supposedly?
Yeah, but the application would have been a portable application. Is that what you're saying? You carry this thing around and set it up somewhere.
Yeah, and that's basically.
So if you got to Mars, you'd want to use it on Mars.
Yes.
And have it so you can move it from one spot to another.
Yeah, it allows it to be more flexible. That's the main thing I kind of noticed with the original designs was they were all set there, and the main idea behind it was set it there, leave it, hit the start button, but don't mess with it too much. And I wanted something that was more adaptive than that.
Okay, thank you.
Do you have any future plans to go out to MDRS, maybe on the astronomy team or something?
I would love to. Right now, my schedule is extremely tight, but hey, if time frees up, I would love to go back. It's a great place. It's beautiful scenery as well as you learn a lot and just a great setup in general. More questions?
So this plot here, you have two separate blue lines there?
Yes, so
Are they just different trials of data, or explain that?
so what this straight line is actually what the oscillator is the MIDAC is outputting to the oscillator. So it's cycling through the different voltages, and then as it goes through different voltages, this is actually changing the frequency that the mixer is mixing it through. So you're going through and analyzing different frequencies. Like I said,
Okay, so the straight line is the response, because the output from the box, and the blue line is the response.
yeah, the axes on this graph are actually not the most descript. After running a few tests, I noticed that, but wasn't able to correct it out there. I have since incorporated more frequency analysis into it after I learned a little more into LabVIEW to help add on to what my advisor has put together for me.
So how does that match up with what you expect?
Around the sun, you actually expect a lot of different frequencies, because not only is the sun consist of hydrogen, it consists of lots of other gases. and just the mass amount of radiation coming from it is going to send off lots of different spectrums. So the nice thing about the sun is almost any radio telescope can observe it no matter really what it's tuned to. Any more questions?
What was the total project cost?
For mine, I think I got it down to about 250. I think I'm done.